Many of my fans have been asking me how sound works, which is why I decided to make this video. Unlike light, I used to find it pretty difficult to understand how sound works exactly. With light waves it's pretty simple. The amplitude of a wave affects how bright the light is, while the frequency affects the color. For example, red has a low frequency while blue has a higher frequency. And then for an image to be displayed on a screen, there are multiple pixels, each of which having red, green and blue lights. Each pixel can produce any color by mixing these three colors, and the pixels altogether can produce any image you want. Pretty simple to understand, but what about sound? You may know that with sound waves, the amplitude controls the loudness, while the frequency controls the pitch of the sound. That's all well and good, but even knowing this, what separates the sound of a piano from that of a violin, for example? Let's say I decide to play an A note on a piano and a violin, and both at the same volume as well. So the sound waves produced should supposedly have the same amplitude, because they have the same loudness, and also the same frequency, because I am playing the same note. But clearly these two sounds will still sound different from each other, so what gives? Also, how come a single speaker can recreate an entire orchestra consisting of so many different instruments just with a single vibrating membrane? Top 10 questions science still can't answer. Actually not really, science can answer them just fine. Okay, so let's tackle the first question first. The reason a piano sounds different from a violin is because of something called timbre. At least I'm pretty sure that's how to pronounce it. One thing you have to keep in mind is that a single piano note or a violin string will not produce just one sound wave, but multiple waves. And these waves may not all be identical to each other, so let's say we'll play the A4 note on a piano. Actually, I just realized that the note block definitely deserves a mention in this video, so from now on I'm gonna replace the piano with the note block. They produce similar sounds anyways. So yeah, anyway, the fundamental frequency of A4 is 440 Hz, but generally when a note is played, other sound waves with frequencies being multiples of this fundamental frequency will also be produced. So in the case of A4, apart from 440 Hz, waves with frequencies of 880, 1320, 1760, etc. will also be produced. These higher frequency waves are called harmonic frequencies. By the way, gonna sidetrack a bit, but doubling the frequency of a note produces the same note but an octave higher. So 880 Hz is still A, since it is double of 440. The next harmonic frequency of A4 though, 1320 Hz, is not A because it's not a double of 880, it is close to E instead. With the next harmonic, 1760, we're back to an A note again since it is double of 880. But the one after that, 2200, is close to C sharp now, and so on and so forth. This shows how the A, C sharp and E notes fit pretty well together and don't clash with each other. In fact, if you play A, C sharp and E at the same time, you'll get a nice sounding chord as you can hear. On the other hand, playing three random notes that clash more together, like A, B and C, will not sound nice to your brain. Okay, back to where we left off. Some instruments will produce more harmonic frequencies compared to other instruments, and this is one of the reasons why they may sound different. The more harmonic frequencies a sound has, and the louder they are, the brighter or harsher the overall sound will be. A note block produces less harmonics than a violin, which is why it sounds duller. Here's an example. I'm gonna play a sound with many harmonics. This visualizer shows all the frequencies that are being produced right now. Now I'm gonna slowly filter out the higher frequencies until only the fundamental frequency is left. Listen to how the sound changes. When there's only the fundamental frequency present, the outcome is just a simple sine wave. It's pretty much never like this with natural sounds, cause real physical objects tend to produce harmonic frequencies when hit or vibrated. You probably know how different waves can be summed together to form a combined wave. If we start with a sine wave and start adding its harmonic frequencies one by one, the summation of the wave will start resembling a saw-like shape. As we head towards infinite harmonics, we'll get what's called a sawtooth wave, or saw wave. This waveform has a typical rich buzzy sound, and is commonly used in electronic music and even in retro game 8-bit music. If we do the exact same thing but omit every other harmonic, so like we'll start with 440, omit 880, add 1320, and so on, the result is called a square wave. This has a different, kind of less bright sound than the saw wave, and is also commonly used in 8-bit music. Can you recognize this? Only real veteran gamers will. All of what I just said is true with musical notes. Sounds that do not have a musical tone, like regular speech for example, will have a bunch of random irregular frequencies that do not form any patterns, and therefore our brain doesn't perceive them as musical. The following are the frequencies of normal human speech. You shouldn't be able to see any patterns here.
Relationships just don't work out because they don't work out, and it's not your fault and it's not my fault. It's both of us together that just doesn't work.
But now see what happens with a singing voice instead.
So what if I'm the monster?
See those regularly spaced spikes there? Those are the harmonic frequencies of the notes that were being sung. Apart from frequencies, don't forget that time is also a factor when differentiating between different sounds. The loudness of a sound and also the amount of harmonic frequencies can change over time. For example, when you play a note block, the initial sound is loud and rich in harmonics, but it very quickly quiets down and becomes duller. This produces a plucky kind of sound. A violin note, on the other hand, starts a bit quiet and actually gets louder after a short while. The loudness stays at this peak up until the player stops moving the violin bow along the strings. This produces a longer, sustained sound. Okay, so hopefully I've explained the reason why different instruments sound different from each other. Now we can get to the speaker mystery that I mentioned in the beginning. One way to help understand why a speaker can produce all sorts of sounds with just one membrane is to take a look at our own ears. We only have one eardrum per ear anyway, which means that if we're listening to multiple instruments at the same time, all those different sound waves entering our ear will result in just one single summation wave produced by our eardrum anyway, which then goes to our brain so we can make sense of it. Just from that one single wave, our brain is then able to recognize all the different instruments that produced it and what notes they were playing, and we are then able to distinguish them from each other. Yeah, in reality we are all pretty big brain. So if we replace all those instruments with a single speaker that is producing just one summation wave, our eardrum should theoretically vibrate in the same exact way and send the same signal to our brain, and therefore our brain shouldn't be able to tell the difference at all. In reality, since we have two ears and not just one, our brain is able to tell where each individual sound is coming from. A sound coming from our right side will arrive at our right ear ever so slightly before it arrives at our left ear, for example, and it will also be slightly louder on the right. Our brain is able to use this information to work out the sound source location. With a speaker, the sounds will all be coming from the same location, which is why it may sound less natural to us. But this can also be partly solved by using a surround sound system. So I think that's all for now. I have more I want to share about how sound works, specifically how it works digitally in computers, but that would take a whole other video. Let me know if you'd be interested in that. If this video gets 1 million likes, I'll get to work on that. Okay, I'ma head out.